Something is happening to our Earth. Powerful cycles are affecting the planet and will change everything forever. Do we even have any influence on the climate? We'll find out today. Let's get right to it. Everything will change over and over again because there are several cycles, some of which span millennia, that we, with our tiny Stone Age brains, have not yet been able to fully comprehend. Some of these cycles take place in space. For example, the movement of our solar system around the center of the galaxy. Then there are the Milanković cycles, which, among other things, cause the Earth's axial tilt to fluctuate due to gravitational influences within the solar system. Other cycles are entirely terrestrial, such as the weather phenomena El Niño and La Niña, which alter the climate of the entire planet, or the cycle of our Earth's core, which is still virtually completely misunderstood. All of this influences every form of life on our planet. Let's start right away with the big picture, the motion of our solar system within the galaxy. Our Milky Way is our cosmic home and consists of an estimated 200 billion star systems. Our solar system is one of them, and all these stars are engaged in a kind of galactic dance, a rhythm known as the galactic year. They orbit the center of the Milky Way, and it takes our solar system 225 million years to complete one orbit at a speed of about 200 kilometers per second. And the universe doesn't end at the edge of our galaxy. There are billions of other galaxies, and most of them are arranged in so-called galaxy clusters, which in turn form superclusters. Within our galaxy cluster, the local group, various galaxies and dwarf galaxies are gravitationally attracted to one another. The strongest effect here is the gravitational pull between our Milky Way and the even larger Andromeda galaxy. The two are hurtling toward each other at this very moment and will merge into a supergalaxy in a few billion years. So we must also factor in our approach to the Andromeda galaxy when calculating our motion. The two galaxies, and we as part of the Milky Way, are moving toward each other at about 109 kilometers per second. But as already mentioned, there are other galaxy clusters as well, and they also influence us with their immense gravitational pull. The other galaxies and galaxy clusters near us all exert a gravitational pull on us, and even distant clusters of matter in deep space exert a gravitational force. Based on our calculations, all these distant structures together appear to cause an additional motion of about 300 kilometers per second. But there is another motion that hardly anyone is aware of, and it is caused by the Great Void. For every atom or particle of matter in the universe that congregates in a superdense region, such as regions with many galaxy clusters, there are also regions that have lost the same amount of mass. Just as a region that is denser than average exerts more gravitational pull, a region that is less dense than average will exert correspondingly less gravitational pull. When you have a large region of space with less matter than average, the lack of gravitational pull acts like a repulsive force, just as the extra gravitational pull acts like an attractive force. In our cosmic neighborhood, opposite the location of the greatest overdensity near us, there is a large void with low density. Since we are located between these two dense regions, the attractive and repulsive forces add up, with each individually amounting to about 300 kilometers per second and the total approaching 600 kilometers per second. So broadly speaking, these are the factors that influence our movement through the cosmos. At this point, you might be asking yourselves, what's the point of all this? It doesn't have any effect on us at all. Studies suggest that our solar system formed closer to the galactic center and slowly migrated outward to its current position in the Orion arm of the Milky Way. It's believed that without this migration, life in the solar system would not have been possible, since it would simply have been too crowded in the middle of the spiral arm or near the center. Furthermore, the motion of the spiral arms themselves is not uniform, so our solar system travels through regions with higher and lower matter densities. Traveling through denser regions of matter can affect the Oort cloud, leading to more frequent comet showers. In addition, the amount of radiation that can penetrate deeper into the heliosphere beyond the sun's protective magnetic field increases, which can have direct effects on Earth's climate and cloud formation. The last time we passed through such a dense field of matter was 14 million years ago, and that coincides almost exactly with the transition from a warm phase of the planet to a cold phase, during which our current polar ice caps also formed. However, according to the researchers, the journey through the so-called Radcliffe wave was not the cause of the climate change, but rather served to further intensify and accelerate it. But let's take a closer look at our sun. It's a gigantic fusion power plant to which we are, in principle, completely defenseless, and of course, the sun's behavior has a massive impact on Earth's climate. But as we've already learned, the sun also protects us through its magnetic field, the heliosphere. The sun's magnetic field arises from complex flows of charged particles that occur within the sun. Although this magnetic field is surprisingly weaker overall than Earth's, it is nonetheless of great importance for the processes in the solar system. The sun goes through an approximately 11-year activity cycle known as the sunspot cycle. During this cycle, the number and intensity of sunspots appearing on the sun's surface vary, which is closely related to the solar magnetic field. And then a remarkable phenomenon can occur, a solar pole reversal. This refers to the moment when the sun's magnetic poles switch places. During this event, the sun's magnetic activity reaches its peak, accompanied by increased sunspot activity and a higher probability of solar flares. These eruptions, in turn, can hurl enormous amounts of charged particles and high-energy radiation into space, thereby affecting what is known as space weather throughout the solar system. Perhaps even more interesting, however, is what's happening right on our doorstep, the Earth's magnetic pole reversal. We too have a magnetic field which acts as a kind of invisible force that protects us from the sun's radiation. It extends from the interior of our planet far out into space. Without Earth's magnetic field, the high-energy radiation would roast us, so that complex life on Earth likely would never have emerged. And our magnetic field isn't stable either. It undergoes continuous change over time and can eventually reverse. During such a pole reversal, the magnetic field goes through a period of instability in which its polarity reverses. This process can take thousands of years and is a slow, gradual transition. During this time, the Earth's magnetic field weakens, allowing more cosmic radiation to reach Earth. So what do the polar reversals of the Sun and Earth mean for us specifically? The solar polar reversal is directly related to activity on the Sun's surface and sunspots. The polar reversal of the Earth's magnetic field, on the other hand, is a long-term process spanning thousands of years. The Earth and the Sun are magnetically linked. The Earth's magnetic field is constantly influenced by the Sun. One of the most fascinating effects of the solar pole reversal is its impact on the interplanetary magnetic field. When the Sun reverses its poles, this change spreads throughout the entire solar system. This can cause the interplanetary magnetic field to change and alter the interactions between the solar wind and the magnetosphere of planets like Earth. The strength and characteristics of the Earth's magnetic field are thus directly influenced by these processes on the Sun. If the Earth's magnetic field weakens, it can paralyze all of our technology and, depending on the intensity of the radiation, also lead to significant health risks. In theory, a weakening of both magnetic fields could, in addition to climate changes, also explain the increased geological activity on our planet. However, research in this area is still in its infancy, so nothing can be said with certainty. Of course, the biggest influence on our climate is the Earth's position, and that too is subject to various cycles. To understand this, let's first quickly explain how the seasons we're familiar with actually come about. The Earth rotates as it orbits the Sun. However, its axis is not quite perpendicular to this orbit. The Earth's axis is tilted by just under 23.5 degrees. One part of the Earth is always tilted slightly toward the Sun, while the other part is tilted slightly away. These different angles at which sunlight strikes the Earth give rise to the seasons. Most explanations focus solely on this movement of the Earth around the Sun, but this is highly incomplete because there are many more celestial bodies in our solar system, and they all interact with one another to a greater or lesser extent. Although the Sun accounts for 99% of the solar system's mass and is therefore definitely the strongest gravitational influence, the gravity of the other objects also affects us. The Moon, of course, but also Jupiter, the heaviest planet, Saturn, and to a much lesser extent, the other planets as well. Our solar system is a finely tuned system, like a kind of cosmic clockwork. They all pull and tug at one another, and this affects the tilt of Earth's axis, the exact shape of our orbit, and the ecliptic plane, the plane of the planet's orbits. Due to the physical influences within the solar system, all these factors are subject to complex but regular cycles, and these are the Milanković cycles. The Serbian mathematician and geoscientist Milanković was the first to recognize this in the 1920s, so we're talking here about several astronomical cycles that have a massive impact on our planet and its climate. Perhaps the most important Milanković cycle is the elliptical cycle. Over a period of 100,000 years, the Earth's orbit around the Sun becomes less elliptical at times and then more elliptical again. When the orbit is more circular, temperatures are more stable. When the orbit becomes more egg-shaped, there are sharp temperature fluctuations and maximum temperatures in both directions become more extreme. We are currently in a slightly elliptical phase. Temperatures in summer and winter weather tend to be milder in the northern hemisphere and more extreme in the southern hemisphere. If the Earth's orbit becomes more elliptical over the next tens of thousands of years, these seasonal trends will intensify. Another Milanković cycle is the precession cycle, which influences Earth's axis. As we've already noted, Earth's axis is tilted by 23.5 degrees, and this is what gives rise to the seasons. As part of the precession cycle, Earth's axis performs a kind of circular motion, and this cycle lasts 26,000 years. In just under 13,000 years, the Earth's axis will have moved far enough in its circle that summer and winter will have completely switched places for each hemisphere. There are countless other Milanković cycles, some less significant, some more so. And the interplay of all these cycles leads to something that is as strange as it is frightening: ice ages. Some of the Milanković cycles align perfectly with the ice ages in Earth's history. For example, there is a cycle in which, over the course of 100,000 years, the Earth's orbital plane around the Sun rises and falls relative to the solar equator. The extent to which this can trigger ice ages is not yet fully understood. And here, one final Milanković cycle comes into play, and it is highly likely to bring about an ice age. I'm talking about the axial cycle. The axial cycle causes the angle of inclination of the Earth's axis itself to change. The 23.5 degrees we just heard about are not set in stone. During the axial Milanković cycle, which lasts 41,000 years, the Earth's axial tilt varies between 22.1 and 24.5 degrees. We are currently in the part of the cycle where the axial tilt is decreasing. With a lower axial tilt, summers become milder. After all, no part of the Earth is now tilted extremely toward the sun. The ice that forms in winter then barely melts in summer and becomes a permanent part of the landscape. As a result, vast areas of the Earth will become covered in ice. The more ice there is on the Earth's surface, the more sunlight is reflected back into space rather than absorbed. This is a self-reinforcing process that ultimately leads to an ice age, and of course we must take into account that human activities are also known to have an impact on the climate. As for the relationship between the anthropogenic greenhouse effect and the Milanković cycles, we're still in the very early stages of research. As if all these cosmic cycles weren't enough, there's also a lot going on here on Earth. Everyone's talking about the super El Niño right now. The El Niño phenomenon and its counterpart, La Niña, are directly linked. El Niño is a climate phenomenon characterized by abnormal warming of surface temperatures in the equatorial Pacific. El Niño is part of the so-called El Niño Southern Oscillation Cycle, which describes the highly complex interactions between the ocean and the atmosphere. During an El Niño event, surface temperatures in the Pacific around the equator rise significantly, leading to shifts in atmospheric circulation patterns that can even trigger various weather phenomena worldwide. Typically, the trade winds blow from east to west across the tropical Pacific, pushing warm surface water westward. As a result, the warm water accumulates, for example, near the coasts of Indonesia and Australia. Over a longer period of time, large quantities of warm water can thus accumulate in the western Pacific, which automatically leads to an increase in surface temperature. The famous Humboldt current plays a key role here, helping to balance temperatures. During an El Niño event, however, the trade winds weaken so much that even the Humboldt current is affected, causing warm surface currents to suddenly flow back eastward again. As a result, the Humboldt current slows down progressively and eventually comes to a near standstill. Off the coast of Peru, the water then becomes very warm, and the cold water from deeper layers can no longer reach the surface. This actually has drastic effects on the environment. Plankton dies, many food chains cease to function properly, and increased evaporation can also lead to heavy rainfall on the western side of the Andes, which in turn causes landslides and flooding, putting the lives of local residents at risk. So along the South American coast, an El Niño event causes the eastern Pacific to warm, and as a result, the water in Australia and Indonesia cools. This usually leads to a high pressure system in the eastern Pacific and a low pressure system in the western Pacific, and the air currents, also known as the Walker circulation, then push warm water from Southeast Asia towards South America. The climatic counterpart to this is La Niña. Between El Niño events, which by the way do not occur regularly every year but at irregular intervals, La Niña also occurs from time to time. This phenomenon is characterized by cooler surface temperatures in the equatorial Pacific. In contrast to El Niño, during which the water warms, the water in the equatorial Pacific cools significantly during La Niña, and atmospheric circulations are strongly affected. This in turn leads to increased precipitation in some regions, such as Australia and Southeast Asia, while other regions, such as North America, tend to become drier. The Atlantic hurricane season tends to become more active due to changes in wind patterns from the surface up into the atmosphere. This is referred to as reduced vertical wind shear, and these are precisely the ideal conditions for hurricanes. Incidentally, it's still unclear to what extent a super La Niña will follow the super El Niño. And now, here's something truly curious and almost eerie. A cyclical signal that doesn't come from outer space but from the Earth's interior. It began in 2019 when Chinese researchers from Wuhan measured some very strange readings in the Earth's core. They discovered a fluctuation that occurs roughly every 8.5 years, something that could be described as a wobble of the core. Overall, the Earth consists of three main layers: the crust, the mantle, and the core. These layers have different densities and varying chemical and physical properties, which are influenced by geological processes such as plate tectonics and volcanism. The Earth's core is the innermost layer, consisting of iron and nickel and maintaining a temperature of about 5,500 degrees. The core is divided into two regions, the outer core and the inner core. The outer core is about 2,300 kilometers thick and liquid, while the inner core is solid and has a diameter of only 1,200 kilometers. This hot, dense sphere plays a crucial role in generating the geomagnetic field that protects us from harmful radiation from space. Previous models assumed that the Earth's core rotates along the same axis as the Earth's mantle, since both layers were thought to have a uniform density distribution. However, the Earth's core may actually be tilted at an angle relative to the mantle. Specifically, the Earth's core is tilted by 0.17 degrees relative to the mantle. The density structures are quite different from what we thought, and the relationship between the Earth's core and mantle must therefore be completely rethought. And as we recall, since the magnetic field arises from this interaction, this could also have significant implications for it. One of the most exciting conclusions from this research is the hypothesis that the Earth's inner core is denser and heavier in the northwestern hemisphere than in other regions. It is precisely this asymmetric distribution of density and mass that could explain why the Earth's core appears to wobble every 8.5 years, and that has truly dramatic implications for numerous other processes on Earth. Take the Earth's axis, for example. If the Earth's core does indeed wobble every 8.5 years, and this wobbling is accompanied by a tilt of the core relative to the mantle, it could affect the stability of the Earth's axis. A change in the tilt of the Earth's core could theoretically cause the tilt of the Earth's axis to change over time as well. This could explain why the Earth's axis is currently moving faster than theoretically expected, and then of course, there's also the potential impact on the Earth's magnetic field. As we already know, the Earth's magnetic field is generated primarily by the dynamo-like process in our planet's outer liquid core. And we also know that this magnetic field is crucial for life on Earth. If the Earth's core shifts every 8.5 years, and in the process, the density or mass distribution within the core might even change, this could obviously have consequences for the convection currents in the liquid core, thereby directly influencing the dynamo process and the Earth's magnetic field. One possible effect could be a change in the strength or direction of the magnetic field, and that, in turn, could affect animal navigation, the operation of electronic devices, and the spread of cosmic radiation. Furthermore, the wobble of the Earth's core could also lead to instability in the magnetic field. An irregular or unstable magnetic field would then amplify the effects of geomagnetic storms, disrupt communication and navigation systems, and endanger the sensitive electronic equipment on board satellites. Of course, we're still in the realm of pure speculation here, and further research will be needed to determine what this new finding means for the Earth's magnetic field. I hope you're now absolute experts on cycles. All these cycles span millennia and cannot be stopped. But it's also clear that human-caused climate change driven by greenhouse gas emissions has a much more short-term impact on our climate and can disrupt everything much more quickly, or even accelerate or intensify existing natural cycles. And since this field is still so under-researched, I don't think we should take too many risks here. What do you think about this topic? Feel free to let me know in the comments. Otherwise, I'd say see you in the next video. Take care, everyone.